Hello everyone, my name is Chen Gu and I'm a Technical Director of Geotechnical Engineering Group of GHD based on Perth office. The majority of this study has been undertaken by my colleague Mr. Joshua Chen, who is based on Hobart office, although I've got the honor to present it here to you today. The topic of this study is dynamic analysis for static liquefaction, factor of safety and triggering threshold values in tailings storage facilities. First, a bit of introduction about the objective of the study. Tailings storage facilities constructed using upstream method are known to have a higher risk of static liquefaction due to the contractive nature of the tailings materials under the foundation of the embankment. And such failures are considered highly critical because of their brittle natures. As currently, the analysis of stability of such facilities are mainly based on limit equilibrium analysis, or LEA, using either the peak or residual shear strength parameters, which will either over or underestimate the actual stability of the system, because the actual mobilized shear strength will lie between these two limits. Finite element analysis or finite difference analysis, on the other hand, when used together with some specific soil models, such as North Sand models, can capture the strain softening behavior at element levels using effective stress parameters. So theoretically, such analysis should be able to capture the actual mobilized shear strength during the process to produce a more accurate assessment of the factor safety against failure. Static FEA or FDA analysis, however, will not be able to run beyond the point of the global failure, where the peak shear strength is mobilized. This is because of the inherent lack of inertia term considered in the equilibrium equation of static analysis. So when the system is approaching failure and when the inertia effect is becoming more and more important, ignoring that will result in the analysis to stop. So it can be shown by the sketch here. See, this static analysis cannot run beyond a point that's close to the actual failure here. The shear strength reduction method has been used by some finite element software packages to estimate the factor safety values. Such method relies on progressively reducing the shear strength to trigger the loss of equilibrium. This process, however, cannot replicate the realistic strain and stress paths leading to the failure. And considering the dependency of the engineering shear strength on actual stress and strain path, so not considering the realistic path will mean that the actual factor safeties under undrained conditions using effective stress parameters cannot be produced. So as a result, available peak resistance and also the factor safety against failure, global failure, are both unknown from such static FEA or FDA analysis. So to solve this problem, the method presented here uses a dynamic finite element method to try to simulate the triggering process beyond the global failure so that the actual factor safety against the stability can be estimated. The dynamic analysis has been undertaken using software RS2 developed by Rock Science. And the reason why this software is used instead of the other more commonly used software such as FLAC and Plexis is because of two things. The first is that this software is relatively user-friendly compared to FLAC. And secondly, compared to Plexis, RS2 has got a North Sand model incorporated into it recently. This is the cross-section used in the analysis. The TSF comprises a starter dam and 5 stages of subsequent raises. The current design also considered a smaller stage 1 batteries and a larger stage 2 batteries for increased stability. The cross-section also shows a few locations along the embankment face, which will be later on used as output points to investigate the result. Also shows in the cross-sections are a few pre-selected failure surfaces, which later on will be investigated for the factor safety against failure. Parameters of the tailings. It is mainly fine tailings with 70 to 85% fines, plasticity index between 6 to 10, SG between 3.08 to 3.36. In situ state parameter has been inferred to be between 0.1 to 0.175, suggesting mostly contractive behaviors. Peak undrained shear strength ratio estimated to be 0.25, and the residual shear strength ratio estimated to be 0.11, based on the state parameter of 0.175 conservatively. And the CSL parameters are first, limiting QP stress ratio under traction compression condition, 1.37, and the intercept of CSL is 1.23, and the slope of CSL, also in the E-log P space, is 0.24. So other Northern parameters were inferred from calibrating the numerically predicted traction test result against the lab result, as can be seen from the next slide. This slide shows the comparison of numerically predicted traction result using Northern parameters against the result from laboratory testing. As can be seen, all three set of tests predicted using the same set of Northern parameters match the laboratory test result fairly well. It should be noted that different consolidation pressures and different state parameters have been used for these three set of tests. The sequence of finite modeling. First, the construction of embankment races and also the tailing depositions are all modeled as fully drained stages using the static analysis. And after that, a series of dynamic undrained triggering analysis in which surface pressure has been ramped up from 0 to 300 kPa in 9 stages. At each stage, the pressure was increased linearly by 2 kPa per second, and then they are maintained at the same pressure level for 100 seconds. The duration of each loading stage has been selected so that the vibration effect can be minimized, while still the total number of increments can be kept at a manageable level. This slide shows the stress path and stress-strain relationships from the numerical analysis. The figure on the left here, this is the QP stress ratio at 3 locations, A, B, and C, as shown here. And the figure on the left, on the right, shows the shear stress against shear strain as the same locations. 3 main features can be seen from these 2 figures here. And the first one is that the drained construction and the tailing deposition stages are all following approximately the K0 line, which is quite low compared to in terms of shear stress ratio compared to instability line, suggesting fairly stable conditions. The second one is that the undrained triggering process all result in increased pore pressure and reducing effective P stress. And then the last feature is that during the undrained triggering process, the Q stress initially increases with shear strain towards the instability line, and once it's gone past the instability line, it starts reducing towards the critical state line, which is represent the strength softening process. This slide shows the development of strain softening zone represented by the Q stress reduction with increasing disturbing load. As can be seen, the softening zone initiates from the area immediately below the upstream of the embankment, and then it propagates towards the downstream and also away from the embankment. You can also see that there's a zone that's reached fully softened condition or critical state condition, and therefore further softening has stopped. Last slide shows the softening of Q stress with increasing disturbing force, and this one here shows the softening of the effective P stress with increasing disturbing forces. Here the colors represent P prime reduction ratio against the original P before the triggering process. As can be seen, by the time when the disturbing force increases to 100 kPa, most of the tailing materials beneath or behind the embankment has reached a reduction ratio of between 60 to 70%. Another question is how we can use the dynamic analysis to estimate the threshold on-drain disturbance pressure or the peak resistance available. By raising the surface disturbing pressure in stages, such threshold disturbance can be identified by the two methods, which is the first one by the appearance of a non-zero residual velocity when the disturbing surface load is maintained at a certain level, or the method 2, which is by the peak shear stress loading along potential failure surface with increasing stages of on-drain disturbances. We will look at these two one by one in the following slides. This shows how we can estimate the threshold disturbing pressure using the first method. The figure here shows the relationship between the residual velocity with different levels of surface disturbing pressure. The figure shows two locations. The first one is at the crest of the embankment, which is called 0 meter location here, and the second one is 8 meter below the crest of the embankment. As can be seen, when the surface disturbing pressure increases beyond 90 kPa, non-zero residual velocity start to appear, which suggests that a global failure along failure surfaces exiting at these two locations may occur when we have surface disturbing pressure beyond 90 kPa. The same trend can be seen more clearly when we plot out the residual velocity against different triggering pressures of different depths for cases with no batteries, stage 1 batteries or stage 2 batteries. First figure on the left is the case without batteries. As can be seen, the triggering threshold pressure is around 90 kPa for all failures. When stage 1 batteries is in place, the triggering pressure for the deeper failures increases to 110 kPa, and when a even bigger stage 2 batteries is in place, the deep failure, any failures deeper than 8 meter depth, has a triggering disturbing pressure that increases to 150 kPa. When we plot all the result into a single figure, we can see clear relationships between the threshold disturbing pressures against the depth of slip surfaces for different scenarios. In general, the surface disturbing pressure, the threshold surface disturbing pressure will increase with the depth of slip surfaces. But it's interesting to know that there's essentially no difference between the two curves representing the no batteries case and the stage 1 batteries case for any failure shallower than 8 meter depth. This is not surprising, considering that the top of stage 1 batteries is actually 8 meter below the top of the embankment. Therefore, any failure shallower than that would not be improved by having stage 1 batches. The threshold surface disturbing pressure and peak resistance available can also be identified by looking at the mobilized shear stress along pre-selected failure surfaces. This figure here shows the shear stress averaged over the entire length of potential failure surfaces with increasing level of surface disturbance for different scenarios. It can be seen clearly that for all scenarios there are threshold disturbing pressures that can be identified at which the peak mobilized shear strength is mobilized. What's more important to know is that those threshold disturbing pressures identified using this method are identical to those identified using the non-zero residual velocity method discussed previously. In addition to predicting the surface disturbing pressure, method 2 also allows the factor safety values to be predicted. The factor safety can be defined here as the ratio between the peak mobilized shear strength against the shear strength mobilized when there's zero surface disturbing pressure. The values predicted by this dynamic FEA is between 1.3 to 1.6 for different scenarios and also different failure surfaces at different depths. Such values are well within the range predicted by LEA method, which is between 1.2 to 2, and this is not unexpected. So this brings us to the conclusions of this study. Firstly, dynamic FEA analysis using North-South model can be undertaken to capture the failure mechanism, including strain softening behaviors of contractive tailings. Secondly, the loss of embankment stability or the initiation of progressive failure can be identified by either the appearance of a non-zero residual velocity or by a peak in the mobilized shear strength averaged along the potential failure surfaces. The estimated threshold disturbing pressures are the same from either method. And also the method can estimate not only the threshold disturbing pressures, but also factor safety values against global stability failure. And compared to the limit equilibrium method, the current method has the potential to reduce uncertainty in the estimated factor safety values, resulting in cost savings. There are also some thoughts about future works. First is that currently only the failure scenario triggered by the upstream loading has been investigated, while in reality other failure mechanisms may also occur due to such as downstream toll excavation, free active level increase, or foundation creep, etc. And all these different failure mechanisms could have different safety margin and therefore should be also investigated. The differences between these different failure mechanisms may be crudely visualized as the difference between the shear strength values obtained from different shear strength testing, such as triaxial compression, triaxial extension, and direct simple shear loading conditions. And also, currently, there's no guideline regarding what could be considered as acceptable or target factor safety values for stability analysis based on this non-limit equilibrium method. This concluded my presentation of this study, and thank you for listening.